Hi, everyone. Welcome to our robotics breakout session. Thank you all so much for being here. We have two presentations from some of our core faculty in Texas Robotics, in addition to two pitches and some graduate student lightning talks that we are excited to share with you all today. So up first, we have Dr. Majewicz Fey, a professor in the Walker Department of Engineering. She is the director of the Human-Enabled Robotic Technology Lab and is a core member of Texas Robotics, where she is the associate director of education. Please join me in welcoming Dr. Majewicz Fey.
Thank you, April. Thank you all for the kind introduction. I'm really happy to give this talk, I started my lab back in 2014, Human-Enabled Robotic Technology Lab, to really try to develop robotic systems that are both enabled by and enabled for humans. And today we're talking about machine learning, responsible AI, and robotics. But responsible is kind of a heavy word, right? Like, what does it mean to be responsible? And that sort of inherently implies that something's good. So how do you define, a system that's fundamentally good? Using some of the buzzwords for the day, if you had an embodied AI system, how would you define that to be sort of fundamentally good? So if you bear with me a little bit, we're going to dive deep into a little bit of philosophy and sort of think about this a little bit. So back in the ancient times, Aristotle was a Greek philosopher, and he came up with this idea of a hylomorphism. So he was really trying to define why humans exist and how they exist. And he believed that there was a body, and he also believed that there was a soul. And the combination of those two things is called the hylomorphism, is why humans existed, is we sort of had this physical body, which was the matter, the potentiality. We had some kind of form, which was the soul that shaped what our bodies did, and sort of the intents that we had. And then the unified combination of those two things was sort of why we were humans and how we came to be. So thinking about this from like an embodied AI perspective, okay, so the idea embodied AI, by definition, AI with a body. So what does that look like in this philosophical framework? So you'd have a robot. The robot would be the body, the sensors, the actuators, the hardware that moves the system. And then what's the form? What actualizes that matter? Well, it would be the AI actualization. So human demonstration learning, vision-based methods, end-to-end frameworks, the things that actually make the robot move. So this is the philosophy. So one of the challenges, though, with Aristotle's philosophy sort of fundamentally is that the body and the soul were codependent. And if the body died, the soul would die, and vice versa. If you could have a soul that died, through bad actions or however else you want to define it, then the body would sort of die as part of that. And the fundamental problem then is this mutual codependence. And so you can see this if you just kind of Google epic robotic failures, and you'll see sort of all these crazy videos of when robots fail. And the challenge is that the algorithms that sort of fundamentally underlie these systems are fundamentally fragile. So any error that you have in your sensing, any error that you have in understanding the environment, any errors in force measurements, that can all create things that don't work. And sort of taken to an extreme then, if you sort of think about this, human body union, then, why do you really need a human here in the first place? So you might have humans for demonstration purposes, but once you develop the system and maybe you can use AI to improve its own code, and then maybe you don't need humans after all. And so you sort of lack this human-centered focus then in this kind of philosophical approach to what makes a robotic system, an embodied AI system. And some of the challenges here are, even though Hollywood likes to sensationalize, this idea of robots taking over the world, there's not really that big of a gap. If you don't need a human in the system in the first place, why need humans at all? And we're starting to see some very real cases of robotic systems, autonomous robotic systems that are causing injuries, that are causing lawsuits for the companies that create them. And so it's definitely something that we need to think about, as robots start to come into the world. So what's another approach? So thankfully, also back in olden days, there was another philosopher that came up with a slightly different take to this hylomorphism, and his name is St. Thomas Aquinas. So his philosophy instead is that the body and the soul sort of equally exist, but it's how they unite together that sort of creates this more perfect form of the combination of the human and the soul, the body and the soul. And that's sort of fundamentally what makes us human. So thinking about robotics and developing robotics from this perspective, you would have things like the AI, the instruments, the robotic end effectors, and perhaps even human biomechanics if a human is in the control loop as the matter, all the things that you could use to create a better system. And what would the form look like? So perhaps the form should actually be human intent, human skills, societal goals, things that actually then shape how we want robots to operate within society, not necessarily for its own sake as independent of us, but if we want robotic systems to actually improve our jobs, improve our enjoyment of society, then that should be central in terms of how we design these systems. So the combination of these two things in the Thomistic approach then is that this combination of sort of this body and the soul is actually what creates a more perfect form of what we can be as humans. So sort of this idea of a symbiotic mastery between human and robot. So this is sort of the idea. And I actually first came up with this pitch last December. I was presenting to a group of surgeons. I do surgical robotics research. And so I was sort of presenting this as a way to think about why it's so important to keep surgeons in the control loop, because they sort of are the soul of the system. If you have fully autonomous robots that do surgery, well, where's the protection for the patient? Where's the protection from the surgeon? And one of the fundamental issues with kind of this idea of sort of this human-embodied AI, or how I presented it back then was surgeon-embodied AI, and we can sort of think of the same thing in terms of human, is that you kind of have this fundamental conflict then, because you have to think about these massive opposing ideals of trying to improve and optimize the matter. So what would that look like? Human safety, having sort of reducing the workload for humans, and that's why we want autonomous systems, because it sort of makes life easier for humans. But then on the other side, what about human agency? What about allowing a human to sort of have charge of what the robotic system does? And really thinking about true human outcomes, trust of the system, and these are sort of fundamentally opposing ideals that are really difficult to balance. Anyway, so this is sort of like shaky ground, right? Because especially in my area, which is surgical robotics, you have timescale issues, you have completely unknown models, you go in and do surgery and the patient tissue doesn't match what you're expecting, and there was no way to know that until you actually got into the surgery in the first place. And that's what sort of raises the stakes then, especially in surgical robotics, to make sure that we really keep humans central in how we develop autonomy. And one of the other things that St. Thomas had said was, whatever is in our intellect must have previously been in our senses. And so with robotics, I think we have a really incredible opportunity to actually capture human intent and human goals at timescales that can enable truly assistive controls and really just change the whole philosophical paradigm for how we view robotics and AI, especially when it comes to very human-centered tasks like surgery. So the rest of these slides are going to be very surgery-focused, since that's kind of my primary area of research. But I'll sort of go through a few cases where, we think about matter and we think about ways to model that, we think about form, ways to model that, and then ultimately moving towards sort of this more perfect form, more perfect hylomorphic symbiotic mastery of the two. So if you look at these two videos, these are videos of experts doing an anastomosis task where they're trying to take that little white tube and connect it to the big white tube. And it's challenging. And you can see the expert, how they're doing it. They're moving actually pretty coordinated. They did drop the needle once, if anyone who's really good notices. They had to go pick it up. But beyond that, this is a simulated model, not real surgery. But they're pretty coordinated in how they transfer the needle and how decisive their actions are. And they do a good job of using both hands together. The novice, on the other hand, struggles. Like, they can't even pass off the needle to the other hand. And so this is a bit of an older slide, but this is sort of an early method that we use to develop to really try to understand sort of the matter, the biomechanics of surgery, how we measure that in a time scale that is appropriate for surgical training and for a robotic system. So we started just by coming up with a basic fundamental framework for bimanual coordination, where your hands could be moving together towards a task. You could have multiple targets. There could be an element of symmetry, like if you're tying a knot, you kind of have this point symmetric movement. And the first thing we wanted to study was really just understanding how humans do bimanual movements. And one of the key features from this work that I wanted to emphasize is that by doing sort of these fundamental low-level human user studies, we actually found limitations of humans that can inform how you do AI assistance. So, intuitively, two-target tasks are harder. We found some things related to higher jerk actually relates to better performance, which is really at odds with a lot of the human motor control literature, that humans move in these sort of like perfectly smooth ways, and that's optimal. We also saw that scaling movements negatively impacts the opposite hand, and my favorite one was that the non-dominant hand performs worse in simultaneous tasks, but it's not true for your dominant hand. So if you have to do something with both hands together, wouldn't it be a great opportunity for the AI and the robotic system to help your non-dominant hand more, right? And we wouldn't have known that if we hadn't, really studied the fundamental limitations of sort of the human matter, right? Anyway, so that was sort of the background there. And where we wanted to move towards next is how do we actually predict this in near real time so that we can do real-time robotic assistance? And so this is some of the results of being able to do online bimanual classification of motion. And let me get a raise of hands. How many people think there's any AI involved here? Anyone think there's AI here? Absolutely not. This is a purely geometrical method. It really only depends on time history of position data, and that's all you need to be able to figure out if somebody's moving in a coordinated fashion or not. And that's all you need. It's really just geometry. There's no AI that's needed at all to be able to, in real time, classify the type of bimanual motion. So in the next phase, we thought, well, this is great. I can measure bimanual coordination in real time, but I don't really care because I want to help you do a better job. So how do I help you do a better job? So here we sort of pulled in our expertise from the field of haptics, which is basically creating force fields for training. And we had sort of people do these very basic bimanual following tasks. We had sort of a planar constraint to keep them in a 2D plane. We looked at things like springs, virtual springs programmed between the two hands. We looked at dampers, which is based on velocity, and that really kind of created these rotational types of movements. We looked at dual springs, combination of all of the above. And we had users, again, a very fundamental user study, trying to understand the limitations of the matter and the opportunities, I guess, of the matter. And we had people do these tasks. So looking at the results, we first figured out that actually some of the subjects were really good at the task and they didn't need our help at all. So we sort of put those aside and looked at just the people that struggled with the task fundamentally. And in looking at their data, we found some really interesting things. So haptics in general helped them perform this bimanual trajectory following task better, which we measured because we knew the trajectory, so we did like a correlation with the trajectories. We found that spring feedback helped with parallel trajectories. So if I'm picking up a box and moving it, spring feedback between my hands is what's going to help me do that. And damping, which is that rotational kind of force fields, they helped shape symmetric movements. So if I'm trying to tie a knot, a suture knot, the damping might actually be better. So then we took this and we actually implemented it on our robotic system that we have in the lab, surgical robotic system, and had sort of this task-specific training where they would get haptic feedback based on if they were trying to move their hands together or not in this peg transfer task, which I thought was a video, but it may not be. Oh, it was playing. Okay, whoops, and I just stopped it. Okay, so we sort of assisted them in doing that, and we saw very statistically significant improvements to their overall scores after this training period. So what's significant about this is the humans did the training with haptics. We took it away in this washout trial. There was no haptics at all. And then in the post-test, meaning even after we took all the haptic feedback assistance away, they actually still did the task better, which is great because that sort of signals long-term learning. Okay, so some other things that we have done to try to estimate the form now, or the intent of the human operator, and I won't go into this in too much detail, but it's sort of a kind of some history of work. We've done a lot of work on trying to determine objective skill in robotic surgery using deep learning, focusing on sort of windowing techniques so we could get our classification in near real time. We've done a lot of work on trying to understand what does coordination and style mean in surgery. So are you fluid? Are you smooth? Are you crisp? Are you deliberate? Do you hesitate? And how do you actually measure that and tie that in with some kind of AI algorithm? So this is where we sort of do all the AI work. And we've even done things where we've been able to identify and correct sort of anxious movements in robotic surgery using adaptive haptic feedback. A few other things that we're sort of excited about right now are not just looking at the current sort of human form and intent, but really trying to predict future motions and future movements. And so we've developed some transformer models to be able to look at future movements, and then based on that trajectory prediction, have been creating adaptive haptic feedback to try to assist the user in doing a certain task. Like, for example, this is a suturing task. And we don't quite have statistically significant results yet for this, but definitely some really promising results that we can improve the user's ability to do the task, so improve the time it takes to do the task by using sort of these trajectory assistive haptic guidances. And another kind of fun one that we did is sort of using a very similar architecture, transformer architecture. We've done some skill assessment and interpretation in robotic surgery, where we've taken sort of predefined gestures. So thank you, Greg, for annotating all of these with all the undergrads that you had back in the day. And we looked at these videos, and we're able to see that there's actually specific gestures that are indicative of experts. So for example, how they reach for a needle, how they push a needle through tissue, how they can transfer a needle from left to right hand. These are gestures that look like, if you're an expert, you kind of do these in a similar way. And what was interesting is the novices, there was only one gesture that our transformer model found was predictive of a novice classification. And this was how they dropped the suture at the end. So if you watch these two videos, you'll see they're just kind of dropping the needle at the end. They're not really thinking too much of it. But then when the expert does the task, and the experts did this in all of the videos, is they carefully place the needle at the very end of the task. And nobody told them to do that. They just kind of did it. And so that's also kind of why it's so important that we don't take the human out of the loop, is that, as a surgeon, in this case, a surgeon would never just drop the needle in a patient. Their soul, basically, of like caring for the patient and wanting to ensure good outcomes prevents them from being that careless. And that's not necessarily something AI can teach, but that's sort of an intuition that we can learn by studying humans and find ways to program that back into our robotic systems. Okay, and so now sort of to the big thing, and Johnny's in the back and he's going to give a teaser for this tomorrow. It'll be great. Johnny, great job. So he just got 2 papers published recently at IROS and Roman. And I sort of like to think of his work as our ability to get towards this more perfect form of the human-robot symbiosis. And he's been developing Gaussian mixture models for this, where we are now modeling the robot state and desired trajectories using these Gaussian mixture models. And what that essentially allows us to do is sort of think about means and covariances instead of just XYZ positions. And so the fundamental framework itself is inherently more generalizable. And so now we can sort of teach our robots to collaborate with humans, to avoid obstacles. So in this case, we are teaching the robot, and there's an autonomous robot arm that's moving. And that's autonomous, the one that you see moving right now with the purple trajectory. And then as the human's kind of coming in and presenting an obstacle for the robot can then sort of move and adapt in real time to this unexpected obstacle that the robot doesn't know where it's coming from. And we've also done this for promoting a more compliant behavior, where we want the robot to sort of follow us in doing a task. And in this case, we're sort of moving a needle around. And I think we've also done this for a rubber band, but I'm not sure I have that video. But we're able to do this by using a gradient descent-based framework to find sort of these optimal trajectories for the robot. And then we use attractive and repulsive potential fields to sort of help the user get a more intuitive understanding about what the robot is doing. And this was his Roman paper, where now we're sort of taking this fundamental framework to actually try to create more collaborative control that's enabled using these Gaussian mixture models. And the idea here is the same, where you have a robot arm that's autonomous and then another human that's joining the task and trying to help do this task. And this is a video of a human that is wanting to do a knot tie with the assistance of an autonomous arm. And they're able to do that more or less successfully. Maybe the tail's a little long, but otherwise it's pretty good. And it doesn't always work. Sometimes, I think in this case, because we don't have a way to measure force or tension information yet in the model, I think in this case we may have broken the suture, and you'll see that in just a second. But it's still sort of a fundamental framework where we can find ways to, adaptively have humans and robots collaborate together in the same space. Anyway, so I think this was sort of the last slide then is some of the next things that we're working on and thinking more towards is that you don't necessarily need just a standalone robot and a human, but we're looking at wearable devices, so like wearable robotic arms, vibration devices on the arms, telementoring systems. And so we're really now thinking about sort of this idea of human-robot teleoperation sort of on the body, off the body, and we're working there. So anyway, so this is the wonderful lab, great students, and if there's time, I'd be happy to take a couple questions.
Hi, thank you. Can you talk a little bit about how the models are trained and if you've done any work with watching videos and that kind of visual learning? Have a model watch 1,000 surgeries and then know how to do whatever? Yeah,
so we never do that. Johnny, you want to answer that? He does lots of knot tying. Yeah. Yeah, so one of the hard things is we do need that data. And you need the data, but you also need the examples to sort of train on, but you also need to make sure that the examples you have contain the data you want. So one of my other students is working on trying to get surgical skill data from the video itself, which is kind of a challenge, and that's a big area of research in surgical robotics in general. Like, can you pull the skill data only from the video, not knowing anything else? But we're really interested actually more on the human side of it and how the human controls and manipulates the master manipulators of the robot. And so we like to collect our own data and use people from the lab or ask our surgeons to come in and demonstrate for us so that we can use their data. But it's pretty data light, I would say, for the most part, what we do. And of course, jigsaw data was a huge help to us. So thank you to Greg Hager.
Mm-hmm. Yeah, thanks so much for presenting. I'm curious to hear more about how the haptics data works. So I imagine there's obviously some sort of spatial component and then maybe some kind of feeling, but how do you know which or how many parameters you're collecting? And like I saw like the remote controls, how do you develop technologies to collect the data that you want?
Yeah, so that's a big challenge, and in my lab we've sort of really just been focused on kinematic data because it's something we can measure from the robotic system itself. So we don't often do much where we measure force interaction data from the human and the robot. We've sort of tried to estimate it a little bit using joint torques that you can calculate from the robot, so you can kind of get a sense. But we never, really put sensors on the human. But your other part of the question, I think, is also related to like, what's good enough, right? And that's the big challenge because humans are different. Their sense of perception is different. And what might work for one person is not going to work for another person. So that's always one of the biggest challenges in doing human-centered work is lots of subjects, lots of surveys, and really just hoping it's good enough. Mm-hmm.
I was wondering, are there any situations where adding AI or autonomy could be harmful, like by over-assisting or distracting the surgeon? And how do you detect and avoid that?
Yeah, no, I think you're absolutely spot on. And that's exactly why I think we got to be careful about it, because there are cases, even but what is the challenge is like, well, you have a human do surgery, the human can make mistakes too, right? Like the surgeon could be tired, too much coffee, and their hands are jittering, so they're not able to sort of cut, or maybe they thought the anatomy was one way, but it was actually a different, unusual anatomy, and they got lost, right? Like they didn't really know what they were doing. And that's really fundamentally the biggest challenge is you sort of have an imperfect human and you have an imperfect robot, but is there not a way that we can sort of use the strengths of both systems to create a better system overall? And so I don't think we have an answer to that yet, and I think absolutely that happens. I don't know if there's any examples of, autonomous surgical robots that have caused problems, but it's definitely something that we need to be mindful of, I think, as we're creating new algorithms and new technology.
Are y'all using any LiDAR kind of data?
We haven't. No, not at the moment. Yeah, one of my students, not for this stuff. We do have a different project where we are trying to do some skull LiDAR to calibrate a robot to a brain, but I can tell you about that later.
One kind of similar question. Thinking about visual servoing. So I know that you were saying you're collecting directly from the arm, which is great, but the surgeon is effectively visual servoing.
Yeah.
Right? So I'm curious if that was something else y'all were looking at.
So that maybe not necessarily to the extent of defining exactly where the robot goes, except Johnny's sort of working on some of the things related to that. We are definitely sort of moving towards an area of using the camera field to sort of understand things that are happening in the world. So one of my other students, Aldo, he's been developing some sort of like contact estimation algorithms where he kind of trained in simulation first contact events and then is trying to predict it in real time with the real robot to be able to provide sort of more contact-based information from the vision itself so that you can then program. But we haven't yet explicitly, I think, controlled a robot to go somewhere based on vision alone. Right? I don't think so. Yeah.
We have time for one more question. Yeah.
Where do you see things headed in terms of being able to do surgeries remotely?
Yeah, so I think sort of the first answer to that would be, well, we've actually done that a long time ago. I think that's maybe one of the first things that got me excited about surgical robotics in the first place is probably in like the early 2000s. I remember hearing about this transatlantic teleoperated surgery. And so they have done that. They have been able to do that. And I think it's a great opportunity. There was a lot of research in sort of understanding time delay and how over a long period of time you could sort of make sure that you could still control the system transparently. Teleoperation I think it's going to come back as a research area. I believe it. But I think there's some opportunities there that it would be worth kind of revisiting what that looks like these days now. Mm-hmm. Yeah. Yeah, the surgeon says no. Sounds good. All right. Well, thank you all so much for being an attentive audience.
Thank you so much.
I appreciate the time.